Yes, thank you very much for the introduction. It's interesting, I have so many microphones, 1, 2, 3, 4, 5 there. You see 2 here. Hopefully everything works. Yeah, it's a great pleasure to be in Korea. I think last year was my first visit after a long time, and I was really impressed by the quality of life in Korea. Everything's so well organized, public transportation, everything, science, very high level. So thank you very much for the invitation to KAIST. With Hanjun, we have collaboration for a while. I've known Hanjun maybe for 15 years or something like that. Anyways, since you were a graduate student in Caltech, I think. So it's a great pleasure to be here. And I will talk, so this is a general seminar, more or less. And you may know that last year's Nobel Prize in Chemistry was given for quantum dots, which is the beginning of nanotechnology. So back in 1980s, people in the United States and also Soviet Union, they asked the question, what will happen to the properties of materials when you make them smaller and smaller and smaller, nanosize. So these were theoreticians just like us. And it was quite remarkable that they could predict something very unusual, that, for example, you can change the color of your laser pointer like this one from green to red by simply changing the size of your material, not changing the material itself, but controlling the shape and the size. And this idea back in 1982 or so gave rise to the whole field of nanotechnology, which started maybe in 1990s, last century, and now it's one of the biggest fields in science, in chemistry and in physics. And so I will talk about 3 kinds of quantum dots. Semiconducting, which is the beginning of nanoscience. This is something that people considered in the 80s. So this would be one example. Then I'll talk about metallic clusters. And they have very special states called plasmon-like states. This is one example. And then late at the end, I will talk about perovskites, which is a material that became popular 10 years ago and is still one of the very popular materials because it has very interesting features that combines features of semiconductors, of molecules, and also maybe of liquids as well. Okay, so this is the outline of my talk. The first part is on semiconducting quantum dots. What people did in those days, they described the properties of the quantum dot, of this crystal, in a very simple manner that led them to think of those particles as artificial atoms. And then, since then, people tried to make molecules of those artificial atoms or some lattices of artificial atoms. But if you look at the typical example as I draw here, it looks spherical, looks like an atom. But in fact, it's much more complicated because, first of all, you have some molecules on the surface that passivate the crystal. So it has some molecular features as well. But at some point, you also realize that you have many, many atoms. So even though overall it looks like a big atom, some spherical shape, it has many, many actual atoms. And in fact, it's very similar to bulk. So the question that I want to address here, how you should think about semiconducting quantum dots, like artificial atoms, the way people thought about this back in the 80s, or more in a chemistry way, because it has molecular features, or maybe the properties of this cluster is not much different from a property of some bulk, large-scale material that gave rise to this cluster. So what happened in the 80s? So people studied semiconductors for a long time, but then they asked the question, what will happen if you make your semiconductor smaller, smaller, and smaller? And they solved a very simple quantum mechanical problem, which is classic, basic quantum mechanics problem, particle in a box. So you have spherical shape well, or box, and then you put an electron in this box or hole. So in bulk semiconductor physics, you have conduction band and valence band. So here you have negative charge electrons, here you have positive charge hole. And then you simply solve very simple quantum mechanical problem when you have electron or hole in a spherical well. And then you get states just like you have in hydrogen atom, SPD states. That's why people call quantum dots artificial atoms. But there are some differences. For example, you know that in hydrogen atom, you can have one s, but you cannot have one p state because you have to go to 2s and then 2p. But basically, it's very similar. You have SPD states. And then the main conclusion that people drew from this picture is that you have energy gap that depends on size. So if you make your quantum dot smaller and smaller and smaller, and this is the quantization, basic property of quantum mechanics, the energy levels become more and more spaced. So you can change the color of your laser pointer from green that I have now to red, for example, by simply growing your quantum dot a little bigger. So this gave people a new handle how to change properties of your material. Instead of changing the composition, for example, you can simply change the size, and then you can tune your material for LEDs. Quantum dot TVs are popular these days. Maybe Samsung actually makes them. Maybe Samsung was the first one to make them. People also use quantum dots to track biological objects because these are very bright emitters. So there are many applications. The question that, as a chemist, so I work in the interface between physics and chemistry. And in fact, people that come from physics and people that come from chemistry, they have different expectations about different properties. Also, even language is different. So for example, in chemistry, we say vibrations, but in physics, they call phonons. Same thing, but so when you have a quantum dot, do they have vibrations or phonons? Or in chemistry, we have some excited states. In physics, people say extons. But it's not just the name, which you still need to learn, but also the expectation. So when you talk about charges, in chemistry, you have very strong interactions between electrons and holes, different charges. But in bulk semiconductors, in physics, interactions are very weak because they are screened. Also, electron vibrational interaction or phonon interactions are very strong in molecules. You can shine light on a molecule, it can change its structure, right? Because your vision, how it works, you absorb light, and then molecule changes geometry in your eye, and this is how the signal is sent to your brain. But if I shine light on some large physics object like this one, nothing's going to happen, right? Nothing. It's not going to deform. Also, if you have a molecule, if you change one atom in the molecule or remove an atom, it's a whole different molecule, has very strong chemical reactivity, radical, etc. But if I scratch the surface of some large object, nothing's going to happen to this object, right? But what matters for quantum dots is size and shape instead of adding or removing one atom. Also, when you talk about molecules, you have very discrete energy levels, just like I drew previously. But when you talk about large objects, physics type condensed matter objects, you have continuum of levels. So here you have many, many levels, but in atoms and molecules, you have discrete levels. So the question is how you should think about this when you study whatever you study experimentally. So when you study spectroscopy, what color my laser pointer is going to emit at, you can take the physics view basically. You ignore charge interactions, you ignore electron vibrational interactions, you define size and shape, and then at the end, although you have discrete energy levels, because the size and shape defines the gap, and the gap defines the color at which your laser pointer emits. But this was all done back in the 80s, and when I started my research, there was a different question, which is now a big question about solar energy, because we would like to replace some fossil fuels and other resources to renewable energy, and solar energy is the biggest source of energy we actually have on Earth, so much sunshine. And people make solar cells, typically of silicon, but ideal silicon solar cell, or even any material that you can use to make a solar cell, its efficiency cannot be more than 32%. Why? Because you have solar spectrum that covers a whole range of energies. So if your energy of this material that you use, like silicon, this gap is tuned to have to absorb in the red, because solar spectrum covers mostly visible, a little bit of ultraviolet, some infrared, but mostly visible light. So you tune your material to absorb somewhere in the red, for example, and then you have much more energy in the blue and ultraviolet side of the spectrum, but all this extra energy is lost to heat. And that's why in a simple solar cell material, you cannot have efficiency more than 32%, some limit, theoretical limit people developed. But people proposed, so people assumed that in quantum dots, this cooling, because you have many, many vibrational many levels, so energy that you have excess in the blue side of the spectrum right here is lost to heat very fast. So all this 70% of extra energy is just lost to heat in a solar cell. They could use this extra energy to excite another electron. And the argument was based on this picture, this particle in a box picture, where you have discrete energy levels. So instead of having many, many states and very fast relaxation, you have gaps between states, and you have very slow relaxation, and instead of energy lost to heat, you can do something else. For example, this kind of process, which also has different names in physics and chemistry, and then people working on this field came up with a new name. And also this whole story actually gives you a very interesting example of how science works, and how you have some discovery, and then you have to revise your discovery, and at the end you converge to something quite useful. So this is so the people that proposed this idea, called multiple exciton generation, came from National Renewable Energy Lab. And because this is national lab in US that makes solar cells or other resources that comes from renewable energy. But the people that first discovered this phenomenon where you have absorbed high energy photon, blue photon, for example, and you create more than one electron hole pair, more than just one electron, one hole, let's say two. They came from Los Alamos, Viktor Klimov, and partly because they used another material that was not commonly used by other groups. And what they report here is the efficiency, meaning how many charges you excite per one photon. And in the simple picture, you can only excite one charge per photon. But in their experiments, they showed that if you excite, so this is your band gap, but if your energy is twice, or better 3 times, like in this picture, your fundamental gap, then you can excite more than one electron hole pair. And then if you keep increasing your charge energy, you can excite more and more. And then almost immediately, people from Andrel, and Efros is one of the people that was at the beginning of quantum dot field on the Soviet side. He didn't get the Nobel Prize, but he was one of those people that developed models. He developed a model of how this can happen, and they measured some time scale. So what they showed is that this happens very fast. You see the time scale is less than 1 picosecond. Picosecond is 10 to the minus 12 seconds. So this is very, very fast. And this motivates actually the kind of study that, the methodologies we develop and the kind of studies that we do and time-resolved experiments that can study such very fast processes. So what was interesting is that, so remember the logic was that relaxation is going to be slow. So instead of relaxing like this, losing energy to heat, you can do something useful. And the argument was that if you make your dot smaller and smaller, you're going to open up gaps, going to be larger and larger. And therefore, this relaxation, energy loss to heat, should be slowed down in smaller dots. And therefore, you can do something more useful than just losses of energy to heat. So Klimov, after he published this paper about multiple excitons, he also published a paper on electron vibrational relaxation, electron phonon relaxation. And he saw the opposite trend. So first of all, the relaxation was also very fast. So I said 1 picosecond, also on the order of a picosecond. People expected so-called phonon bottleneck, very slow relaxation. But here it was also fast. Moreover, when he made quantum dots smaller, smaller, and smaller, relaxation became faster. So this logic that you open up gaps in smaller dots and relaxation will be slower totally did not work. It was the opposite. So that was already a puzzle. And then Munjiba Wendy, who actually got Nobel Prize last year for quantum dots, published this paper saying, oh, the efficiency is 0. So the first reports said 200%, 300% efficiency. But then there was this paper asking how to interpret the experiments. Basically, the experiments were fine, but the way you interpret the experiment depends on your model. And he used some other model, and he said, oh, the effect actually is very small. And in science, actually, it's quite hard to publish negative results. So the fact that there is a negative result paper, it's already quite unique. So what happened is that Klimov came back to his experiments and developed a new model where he involved some new states, new processes that he didn't consider at the beginning, as I will explain. Experimentally, he says, oh, if I stir my quantum dots, or if I don't stir your quantum dots, I have different signals, meaning you shine light on your quantum dot. If you stir, meaning you put quantum dot all the time, new quantum dots all the time. But if I keep the same quantum dot statically and keep shining light, I have a different result. And something happens to your quantum dot. And if he does this stirring experiment, he gets something that works better than if he does the static experiment. So he reinterpreted the experiments using some more advanced models. And he said, oh no, it's not initially ideal behavior was very steep, very efficient. But then with real situation, he reduced the estimates to maybe from this would be 240% or so to maybe 140%. Still effect is there, but not very high, not as high as initially was assumed. So then people wanted to see very slow relaxation of energy to heat. And there was this paper by Philippe Guillot-Sionnet that was published in Science. And he had to make a very complicated system. So he did see, so this is again picoseconds, yeah. But instead of having 1 picosecond relaxation as Klimov, he made this complicated structure, and he was observing 1,000 picoseconds, so much longer time scale. But what he needed to do, he had to separate electron in the core of your system with multiple shells, and then he had a ligand on the surface, and this surface trap created separation of positive charge hole with negative charge electron, and by separating electron and hole, he could achieve this so-called phonon bottleneck, where relaxation of the electron was very slow. And then in 2010 or so, finally people could, so all this was done by optical experiments, but in a solar cell you need current. So ultimate proof of this phenomenon has to be shown by some current measurements. So in this case, they converted photons into current, and they could see that this conversion, absorbed photon to current efficiency, could be more than 100%. So the effect is there, but again, it's not 300%, it's maybe 150% or so. So what's going on? So I was lucky enough to observe all this. In fact, I invited Nozick and Klimov to give talks, seminars, physical chemistry seminars. And I was thinking about this, and the explanation is actually quite simple as soon as you start thinking atomistically. Because the way people thought about quantum dots initially was this particle in the box model. You have a spherical well, you have just one electron, and you have energy levels. Just like hydrogen atom, you have one electron, you have SPD levels. But if you start to think atomistically, you realize you have some crystal that has maybe 100 atoms. 100 atoms has, maybe each atom has 4 electrons, so you have 400 electrons. So you have 400 occupied states, 400 empty states. You have many, many excitations. So this very simple picture of individual levels, SPD levels, actually becomes more realistic, where under each signal, and this is our calculated spectrum, just like they predicted particle in a box model, you have peaks, but under each peak, you have many, many excitations. So you have these SPD states that give you envelope functions, but under this envelope function, you have many, many individual excitations. And if you think about relaxation, you have many, many states, and charges, excited charges can relax very fast and give energy to heat. And that's explaining why electron vibrational relaxation was very fast, picosecond. And that's also explaining in part because why exton, multiple exton generation is not very, very efficient as initially thought. But there's another part to the story. Yeah, so basically, you have this simple picture, ideal quantum dot picture, atomistic picture changes it to real quantum dot picture, and this now explains many things. Yeah, we did show this phonon bottleneck, which I'll skip. Now the question is, if relaxation is very, very fast, how is it possible that you can still create charges before energy is lost to heat? So there are two mechanisms that people discussed. In physics, people call impact ionization or inverse Auger mechanism, where even if you don't shine light, you just have a current, like in LEDs. You inject electron and hole, and they emit photon. So you can have electron and hole injected, but if they have enough energy, then they can collide. So you have high energy electron collides with the hole, and this extra energy goes to excite a second electron. So in this kind of stepwise mechanism, you can create charge carriers that you can create more than one electron hole pair eventually. So how does this work? So we did calculations with Dr. Kim. What's interesting is that he developed a very simple understanding of what's happening, because you have single excited states, and then you have double excited states when you have 2 electrons excited. At low energy, everything is single excited state. You don't have enough energy to excite 2 electrons. But at high energy, you have many more double excited states than single excited states. Meaning that even though you can excite single excited state, because you have so many more double excited states, just statistically speaking, all the population is going to go to double excited states. So what happens in experiment, and this is a small quantum dot, so energy is high, but in experiment they're larger, but the same principle works. You excite about this threshold, so you have this threshold, which is quite universal for any material, any quantum dot size. So if you have band gap of 2, and this is a little less than 3 band gaps, like in the first experiment I showed you, if you're above this threshold, you have single excited state that go into double excited state, just because they have many more double excited states. Then over time, energy is lost to heat, it's true. And then at some point, when you cross back and you lose more energy, your double excited states disappear, and you go back to single excited states. So this is one mechanism, but there's also another mechanism that we developed, but this is efficient for small crystals mostly. So this very simple picture, single electron picture, where you have one electron excited or two electrons excited, it's too simplistic. In the chemistry view, the single excited states and double excited states, they're coupled, which this kind of picture is very common in chemistry, but not so common in physics. And when you have double excited state coupled to single excited state, this double excited state that's dark, usually, it cannot absorb photon, it can borrow intensity from single excited state. And because it can borrow intensity from the single excited state, you can immediately create 2 electrons per 1 photon absorbed. So you don't need any intermediate states. Immediately you absorb photon and you create double excited state. And this can explain why, even though relaxation, energy loss to heat is fast, you can still have double excitons. So this is exactly the material that Viktor Klimov reported first for this phenomenon. What we see in this material, that at energy that's high, so that's where you have enough double excited states. Your all excitations, this is fractional multi-excitons. All excitations become double excited states. So in this particular material, because of its structure, at high energy, you excite double excited states immediately, like I just described, because they mix a little bit with the single excited states. But in other materials that people also studied, but did not report multiple excitons initially, you have a similar behavior where you start seeing double excited states, fractional multi-excitons is large, but you also have single excited states and various mixtures. So this very special material was particularly efficient, and that's when discovery was made because of its particular electronic structure properties, where you excite immediately into double excited states. And last point about this I want to make. So how did people have to revise the experimental data? Right, so you store your sample, you don't store your sample. How do you store your sample on a computer? Right, we're doing some calculations, so we need a model. So the model is that, in fact, the quantum dot model involves some extra states. So what's possible, and I mentioned, I mentioned before here that in order to see this bottleneck, Philippe Giotzionet had to separate charge. He had to separate hole from electron, extracted, meaning that you have extra charge here. So what happens if you have a charge in the core, and this is in this calculation, you have another type of excitation. So you already have electron in the conduction band, and you can excite it. And then you have electron in the valence band that you also excite. So this is your double excited state, but this is not the state that you need for solar energy, because to make it balanced, to make charges flow, you need the same number of positive and negative charges. They have to balance. So this is your double excited state on the right, but this is not the double excited state that you need for this effect to matter. And this happens because your quantum dot is not ideal system. You have some trap states on the surface, and that's why you trap hole, and you have extra electron here that can be excited. So what happens is that when you stir your quantum dot, you don't allow this. You only have this kind of double excitation. But if you keep shining light on your quantum dot many times, you damage it, so one of the charges is trapped on the surface, and you have a new kind of excitation called trion. You have 3 charges, 1, 2, 3. And this needs to be included into the interpretation. And in our calculations, basically the energy where we first saw double excitons that matter, you see this trion-like excitation that totally dominates. And you see the multiple excitons that you need at much higher energies that are irrelevant for applications. A couple more points, just to emphasize the fact that quantum dots are much more complicated than this very simple initial model that gave rise to the whole field of nanotechnology that got Nobel Prize last year. So this was collaboration with Todd Krause in Rochester, where he could make quantum dots in a very controlled way. And what is shown here is spectroscopy spectra. So the red line is emission, black line is absorption. And so as you can see, he can grow quantum dot larger and larger, adding more and more layers. So the black line absorption shifts to longer wavelengths according to this particle in the box model. But emission, first of all, emission shows 2 features. You have this sharp peak, which also follows particle in the box model. But it also shows this very, very broad feature, which cannot be explained by simple particle in the box model. And what's even more interesting, if you put, so the way he makes this quantum dot, which is made of cadmium and sulfur, there are 2 precursors that he mixes and some chemistry happens in solution. And then he stops it by cooling down. But then he can add extra precursor that has sulfur. So he covers the surface of the quantum dot with sulfur. And then emission basically disappears. And then he adds precursor that has cadmium, and emission is recovered again. And he can do it repeatedly. So the question is, how come you have this new emission that cannot be described by particle in the box? And how come emission quenches if you have sulfur, but it works well when you have cadmium? So in fact, most quantum dots that are good emitters, they have metal on the surface. Why? Because metal and non-metal, sulfur, they have very different chemical properties. So the issue is that if you have non-stoichiometric composition, you have some bonds that are not formed. You have some atoms that still need to make bonds, but they're not formed. And this creates mid-gap trap states. So when you have sulfur, it really needs to make covalent bonds, very directional bonds. So if you don't have enough cadmiums to saturate sulfur bonds, you have these trap states everywhere. But if you have cadmium, it's more spherical, it's a metal, right? Metallic bond is much more kind of spread out and uniform and spherical, symmetrical. So cadmium-rich surfaces can heal a little bit. So you still have mid-gap trap states, but they're not distributed everywhere. They are able to heal, and they cluster. They make some subband. And what happens is it's transition between this subband and the regular band that gives you this very broad feature, first of all. And second of all, in sulfur-rich, you have many, many states in the middle, and the electron just relaxes very, very fast. So you don't have enough time to emit light. Everything goes to heat very fast. But in cadmium, you still have some energy gap that's maintained right here. And because of this, electrons don't go give energy to heat right away. They can emit light, and that's why cadmium-rich dots can emit light, but non-metal sulfur-rich dots cannot emit light. And very, very last part of this longest topic of my talk is this is collaboration with Tim Lian, who is now chief editor-in-chief of Journal of Chemical Physics. By the way, what he did, he wanted to study this so-called Marcus model. So when you want to make a solar cell, it's not just that you photoexcite, you need to extract, you need to separate charges. So you have this quantum dot, and then he puts a molecule, and he extracts electron by transferring it from the quantum dot to this empty orbital of the molecule. And he wanted to study this as a function of gap from here to here, called driving energy, delta G. And in Caltech, there's another Nobel laureate, Rudy Marcus, who is, I think, past 100 maybe. He's pretty old, but he's still around. Yeah, he's already turned 100. Yeah. So he predicted, he developed a very simple model, another theorist, a long time ago in the 1950s or early 60s, which is now very widely used. It was very simple, so anybody can understand, and also predicted something that was unexpected. So what's the model? So you have initial state and final state. So you want to go, electron has to go from here to here. And you want to increase the gap. So you want to have your final state lower and lower. So your everyday expectation is that if your slope is steeper, everything is going to go faster, right? So if you have a ball, it's going to roll faster. You're going to slide down your slide faster if it's steeper. But he predicted so-called Marcus inverted regime, meaning that if your gap is too large, it's going to turn over. So very simple model. You have initial state, parabola, final state, another parabola. The parabola represents vibrational motion. Vibration is harmonic. And then there is some energy barrier between. So if your final state is high, you have a barrier. If you bring your final state lower, you have no barrier. But if your final state is too low, then your barrier disappears completely. Oh, sorry, then your barrier, so eventually, first it disappears. Yeah, okay. Here it disappears, and then if your final state is too low, it appears again on the other side. So the point is that if your final state is too low, if your slope is too steep, actually you create a barrier again, and the dynamics slows down. So Marcus model predicted this inverted regime, but when Tim Lian wanted to see this with quantum dot, instead of having inverted regime, he was seeing saturation. Why? And again, this is a very famous model, Marcus model. So you'd like to understand what's going on, how you need to modify the model. So what happens is that you need to consider a different process that usually you ignore in molecules, meaning that when your electron goes down, normal model assumes energy goes to vibrations. But in nanomaterials, you have pretty special situation. You have very many states, so like small pieces of bulk. You have high densities of states, many, many states. And you have charges that interact. So you have a positive charge present here. And because charges are next to each other, in bulk material, in a piece of metal, large wire, charges are far. Positive go one way, negative go a different way. But here they're close to each other, so they interact. So the energy of the electron can go and be exchanged with the energy of the hole, positive charge. And therefore, you need to modify the model because your intermediate state involves hole excitation. So he developed a model and showed that you have a hole excitation first, and then electron goes to vibrations. And this hole excitation only lasts for 2-3 picoseconds, and then it disappears. So on a normal time scale, everyday time scale, you never know that your hole was ever excited, but it explains the difference in the dependence of this rate on the energy gap between initial and final state. So we had to modify Marcus model to include this hole excitation to allow to explain this process that you don't have turnover, but you have the saturation. Okay, so this is the end of the first part, which took me 35 minutes almost. So then second part, plasmons. I know many people who had very nice discussions today, metallic particles. So metallic particles, the question that you may ask is that in a piece of metal, you have no energy gaps, everything goes to heat very fast. But there could still be some processes that involve electronically excited state. Guess one of the main messages is that you have very special states in metallic particles that form so-called plasmon excitations. All systems have this kind of states. In atoms, they're known as Rydberg states. But in metals, they're at relevant energy range, at energy range that is visible light, for example. And these states, they extend very far from your material. So I'm comparing now what I call bulk state in the metal cluster, surface state that's on the surface, and this plasmon-like state that extends very, very far. So there are two things that it can do. First of all, it can help to transfer charge over long distances or do something over much longer distances. If you look at this projection, basically this is angstroms, 10 angstrom is nanometer, so it extends more than nanometer away from the atom. And the density is less in the middle. On the atoms, you have less density than very far from the atoms. So it can facilitate something very long range. And second, electron vibrational interaction is very weak because it's not on atoms anymore. So when we talk about hot charges, energy lost to vibrations, electron vibration coupling is weak. So the height of this red peak in the left plot is low. And because of that, you can expect longer lived excited states. And you can maybe do some interesting photochemistry with so-called hot electrons. The question is, so when you make a solar cell, you have some molecule or semiconductor that absorbs light. And then you want to separate charges like I showed you before. So charge could go from your chromophore into some other material like another semiconductor. But people started to use plasmonic particles that are pieces of metal. And normally you don't make a solar cell out of metal. You make solar cell of silicon, which is a semiconductor. But they could see that you have charge transfer from metallic particle into semiconductor with the high efficiency. And the question was, how is it possible? And traditional mechanism was that you excite. So plasmon is a complicated physics concept. It's a wave of electrons that goes in and out of the surface. Many electrons involved. But on a very fast time scale, 10 femtosecond or so, this coherent wave becomes incoherent. So it loses coherence. Basically, you have an ensemble of particles. And then electron can be injected from this metallic particle into semiconductor. But the question is, how come it goes to the semiconductor even though it's a piece of metal, everything should relax very fast, there are no energy gaps. So what we saw in this work is that you have, your photoexcited state that has this plasmon-like character. You have this special kind of density that extends far from the metal, but it has a very long tail. So what we said in this paper is that you immediately photoexcite a state that is partially charge separated. So maybe 20% of your charge is already inside the semiconductor. So this problem that you have charge in a piece of metal that's going to relax very fast is not a problem anymore because your charge is already, there's a 20% chance that your electron is already injected in the semiconductor. So you excite charge separated state. And 1 year later, so that was 2015, there was the science paper by Tim Lian. So in this case, we did not collaborate with him, unfortunately. We should have waited and collaborated, talked to experimentalists more. He basically publishes the same result, but experimental. This is his picture, very much the same picture. You have excited state that involves charge transfer from your metal to the semiconductor. And how he proves it, so in the traditional mechanism, when you put some photon of a given energy, energy tells you difference between electron and hole. So you excite the electron from here to here. But whether or not the electron is above the conduction band edge is kind of random. So you have a distribution of charge carriers, and some are above and they can be injected, some are below this edge, cannot be injected. So therefore, traditional models, different models give you different dependence, but they give you dependence on the energy of your light, photon energy that you send. But in his experiments, he saw no dependence down to some threshold, and this threshold was exactly the energy from this Fermi level of the metal to the conduction band edge of a semiconductor. So this was experimental evidence of this kind of charge-separated excitation. And then we did this for 2D materials, and there's a big difference because when you have TiO2, and in the data that Tim Leon reported, he grew gold on cadmium selenide. Basically, he took 3D material, there was a surface of 3D material, and then he put metal particles on top. But people could also do this for 2D materials. And the difference is that 2D material surface is very saturated. Why it's 2D? Because it's chemically happy. Versus 3D material like TiO2, which has unsaturated chemical bonds. So the interaction between gold and 3D material, surface of 3D material, is much stronger than interaction of the same kind of particle on 2D material. And you see this yellow extends everywhere, but this red extends a little bit. So this contribution of charge-separated excitation is much less because you see much less red density here of 2D material than this yellow here in 3D material. Again, because interaction at the surface is much weaker because surface is happy. It's fully chemically saturated. And this is collaboration with Jihan Lo. It's an experimentalist in Singapore. So he can do many interesting things. So in this case, he could measure 3 things. He could measure location, time scales, and distance. So what happens in this case, he excites electrons in gold. And then he could measure charge transfer from gold into this 2D material, MOS2. So he could measure rate. And this is now rate. On the y-axis is rate in the middle. He could measure distance. How he measures distance? He can measure rate at a given location, and then he uses some kind of probe that could push your MOS2. So this 2D material is a very perfect material, but gold has some corrugation. So the distance between gold and 2D material changes depending on location. So he could push and see how far he can push, and this way he can measure distance at different locations. So eventually he plots a rate of charge transfer versus distance, and he sees this dependence, which is weak. So if you study this in many materials, you expect this dependence to be very sharp, like at the end. But for a long time, it's not sharp. And basically, it's almost like you have some conjugated bridge. If you study molecular systems, you have donor acceptor and conjugated bridge. So this is not sharp. So how is it possible if essentially you have vacuum, nothing between gold and MOS2, just vacuum? Why is this so? This dependence is not very sharp. And this is, again, this kind of extended state. So as I told you before, you have this very special plasmon-like orbitals, Rydberg states and atoms, but in metals they make plasmons. And they extend very far, and they overlap. So you have your plasmon-like state that overlaps with the state in your 2D material versus regular normal state that does not overlap in this vacuum. And exactly the extent is about maybe 1 nanometer or 0.8 nanometers. So as long as this state extends far, you have this weak dependence. And then after 8 nanometers, this state disappears, and then you have very sharp dependence. So this is a very interesting state. And the last example would be a paper which I'm proud of. First of all, different reasons. One is that we had to develop methodology published in this paper of my PhD advisor when he was in the special issue dedicated to him when he turned 70. Second interesting thing, this is now collaboration with the engineers, which are very practical people, but they also use different language. So when we talk about coupling, electron vibrational coupling, we talk about some electron volts, units, but in engineering, everything is heat capacity, basically. So we had to use their language and our language and combine them together because they talk about energy flow, and the rate of energy flow is basically heat capacity, right? How much heat you need to put to raise temperature by 1 Kelvin and so on. But what was the application? The application is, so heat dissipation is a big problem in electronics, right? Everything's overheating. Electric cars can catch fire because battery is overheating. So you need to dissipate heat. So they want to make a heat diode. So normal diode, you have electric current one way and not different way. But you want to do the same with the heat. How do they do it? So you have a piece of metal, gold on the left, and then you have a semiconductor, and then normally you have another piece of metal on the other side. And what happens, you have electrons in gold that they're hot. And then you have electrons in the semiconductor that are, because it's some doped semiconductor, intrinsically you have electrons in the conduction band. So what happens is that electrons in the metal that are hot scatter. They exchange energy with electrons in the semiconductor. And we showed that it's not electron transfer, it's actually scattering. It's just energy transfer. And then you have another piece of metal. The electrons here can scatter with cold electrons in the semiconductor. And they cannot give energy back because this is band gap. There's no charges here. And so this paper showed that you can make a material that can be basis of thermal diode. And you have energy transfer one way, heat transfer one way, and not the opposite way. So perovskites is a modern topic. Very interesting material. So first of all, what's perovskite? It's a crystal structure, and it's the most common crystal structure on Earth because it has many different possibilities. First of all, it has 3 elements, A, B, X, and there are many different structural phases. So it's the most common crystal structure on Earth. We study a particular perovskite called metal halide perovskites because they have halogen, or halide, as one of the key elements. Also the name, so the name comes from some rich guy, right? This was 19th century, there was no science foundations. All the research was funded by rich people. So there was a rich guy that wanted to look for some minerals, I don't know, diamonds, in Ural Mountains, separate Asia from Europe, right? And so he funded some research, and some scientist, geologist, found some mineral and named it after the rich guy that gave the funding, yeah. Okay, so that's Perovsky was the name of that person. What's interesting is that they combine features of inorganic materials, molecular materials, even liquids. So first of all, what's the structure? So you have 3 elements. You have this red, green, and there's something in the middle here. So red is lead, and green is iodine in this case. So you have a very nice crystal lattice, inorganic lattice, just like silicon or any other inorganic material. Because of that, it conducts charges very well, right? Most materials are some very ordered conductors, right? Semiconductors, very ordered inorganic materials. You can have organic semiconductors too, but they're not as efficient as inorganic semiconductors. But you have this molecular thing in the middle as well. So this is some molecule. You can vary the molecule. So it's a small organic molecule. So it has organic features too. And moreover, this organic molecule, it has some dipole moment. It has some non-equilibrium charge distribution. And it can rotate quite freely. So if you come from liquids, as my PhD was on liquids, you call it solvation. Again, language difference. In physics, you call it polarons. When you put a charge, the environment, the atoms around it, they change the structure. In liquid, you call it solvation, right? If you have positive ion here, your water would point oxygen towards the cation, and vice versa. So the same happens here. But the size of this polaron is very large. So in a liquid, you have first solvation shell, second solvation shell. They will modify in response to a charge. In this case, you also have very large response of your material to charge. If you look at silicon and other material, you don't have such a large response. You put charge in silicon, structure may change, maybe locally, but not on a global scale. But in this case, structure can change quite a lot. And moreover, it's probably a joke, but some seriousness to the two. So main thing about semiconductors, you need to get rid of defects. If you have unsaturated chemical bonds, some non-stoichiometric composition, you create trap states and charges get trapped. But perovskites are very efficient. Immediately they became efficient, and that's why they are such a popular material. And people are wondering why. So it's as if they don't have defects. And I kind of joke that if you have a liquid, liquids have no defects, right? If you're missing an atom in a liquid, it kind of flows and fills out that point. So maybe this is a little bit of liquid property here as well. Okay, so what's going on? So you have those trap states. I already talked to you about them when quantum dots don't emit light because they have mid-gap trap states. So perovskites also have some mid-gap trap states. So this is, so you basically have iodine. So this is the composition, lead, iodine, and this organic molecule. And iodine can be missing or it can be like extra iodine somewhere. So when you have extra iodine interstitial, it creates this trap state, which is kind of close to the valence band. So people say defects in perovskites are shallow. But this is, in a way, vague statement, as I'll show you. So indeed, this trap state is close to the valence band, but this energy gap is still pretty large. So first we did calculations, and what we saw was quite interesting. In a normal semiconductor, you have positive charge in the valence band, it gets trapped. If it's trapped here, it never escapes. It usually recombines with the other charge. But in this case, it actually can escape before it recombines. So it's trapped very fast, 0.03 nanosecond, but recombination is so slow that it has enough time to escape. And initially we thought, oh, this is because you have this very sparse structure, and you have very localized trap state. So the overlap of this trap state with the state of electron with which it has to recombine is small, and therefore this matrix element is small, and so it does not recombine, so it can escape. But what we realized a little later is that dynamics is important. So if I look at this defect state, extra iodine interstitial, its energy level, this red line on the left, it fluctuates a lot. So when people say, oh, defect is shallow or defect is deep, it's a very vague statement. If you do calculation on some optimized structure at 0 temperature, this is very different from what the material does at room temperature. So in this case, the defect energy level fluctuates so much, half an electron volt, even more. Sometimes it's very deep, sometimes it's very shallow. When it's very shallow, charge can escape. And this is quite different from what you see in other semiconductors because they're not as soft. So this material is much softer than silicon, 10 times softer. So it can fluctuate and respond very well. And you look at other defect states also. Maybe on average it's deeper, but still sometimes it's very close to the edge of the band and charges can escape. So when people develop models and they say all defects in perovskites are shallow, maybe they're deep, but effectively they can become shallow sometimes because of fluctuations. And in terms of how it behaves as a semiconductor, all defects are shallow. So this is another example. If you charge your silicon, let's say, or some normal inorganic material, nothing is going to happen. It's going to stay stable. But because this material is soft, it becomes more like a molecule. So what happens in this case, now I'm missing iodine. So one place you have extra iodine, here I'm missing iodine vacancy. So between those two lead atoms, there used to be an iodine, this purple line, purple atom, but it's not there. What happens is that if you charge, you create defect states. If you just have neutral system, missing iodine, no big deal. But if you put an electron or even 2 electrons in your system, basically if you start running a solar cell or LED based on this material, an electron can be trapped between 2 leads. Leads are positive, electron is negative. So instead of iodine, you have I minus, you have electron minus. And this electron minus can create a new bond. But the difference in the lead-lead distance is huge. 1 angstrom for bonding, it's a very big difference because bond length is on the order of 1 angstrom. So you create a new species, which is not happening in normal semiconductors, but it happens in molecules. When you put charge in the molecule, you can dissociate the molecule, CO2 reduction, and so on. In this case, it responds like a molecule, creates a new chemical species, and then you create mid-gap states and lifetime of charge carriers changes and so on. Yeah, maybe I just stop. If you want me to talk more about perovskites, let me know. But it's a very interesting material. So to summarize, I talked about 3 different kinds of nanoclusters. Quantum dots was the beginning of nanotechnology. Back in 1980s, theorists came up with this idea. They asked a very simple question, fundamental question: what will happen if you reduce the size of your bulk material to something on the order of a few nanometers? And then they came up with this very simple model that says, oh, I can change the color of my light being emitted depending on the size. So basically it created a new handle how to change properties of the material. But although this was very good for describing emission, LEDs, etc., and it started the whole field of nanotechnology, reality is much more complicated, and that's where chemistry becomes important because you need to worry about the fact that you have some ligands on the surface, that you have many states, you need to think atomistically and so on, which is what chemists do. And this totally changes the way you think about quantum dots, at least in terms of solar energy applications. So the second part was plasmonic particles. So here, the main message, you have very special states that extend very far. They have very weak electron vibrational interaction. And because of that, you can have some new phenomena. You can maybe do excited state chemistry, or you can charge transfer over long distances because of this kind of states. And perovskites, very interesting material, still very popular. Actually, all of these are still hot topics. And it combines properties of inorganic solid state matter, some organic matter, and even liquid matter. I don't think there's any other material that has this kind of combination of properties. The main problem is that they're not very stable, but people can fix stability by some saturation of the surface and so on. But from the fundamental point of view, they're very, very interesting. And I'm going to stop here, so thank you so much.